The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to this webinar. My name is Michael Evangelista and I will be your moderator for today. Just a few reminders that you are in listen-only mode to avoid unnecessary background noise. However, you can type in your questions anytime you want in the questions box and those questions will be answered by our presenter at the end of this presentation. By the way, the recording and certificate of this webinar will be sent out in 2 days' time. And our topic for today is about the partial discharge measurement on gas insulated switchgear or GIS. And it will be presented by one of the applications engineer from Megger, India, Mr. Kior Patel. So Kior.
Yeah, thank you, Michael. Thank you for introducing myself. And as Michael said, welcome all. And today we are going to discuss about the partial discharge measurement on gas insulated switchgear. So as a part of today's webinar, we are going to discuss on the following topics. The first thing is the partial discharge measurement on gas insulated switchgear, scope of application. Then what exactly the partial discharge is and how it can affect the insulation system of gas insulated switchgear. Then what kind of different sources or defect can generate a partial discharges in GIS, followed by the measurement techniques for detecting that that partial discharges in GIS. And as a last topic, we are going to introduce the solution what we provide for a portable or online continuous measuring instrument for performing this partial discharge measurements. So coming to the first slide about the scope of application. So if we see for the GIS particularly, this particular partial discharge measurement test is almost as a part of a type test during the development of GIS. Then it is followed during the manufacturing stage as well as a routine test. Then once the GIS is supplied to a site where it is going to be installed, so during the site commissioning it is a part of an on-site test. So it has to be performed prior to charge the GIS or taking the GIS into the operation. And once the GIS is already in the operation, it can be done as a part of a maintenance depending on the interest of a GIS operator, which can be a check, a normal check at a service voltages periodically, or it can be a continuous online monitoring system which is continuously monitoring this partial discharges. So partial discharge is a kind of a test which is really important in case of a gas insulated switchgear. Then now coming to the understanding that what exactly the partial discharge is. So if you follow the definition from IEC 60270, it says that partial discharge are a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. That means when the voltages are present on any insulation, the voltage stress across the any cavity exceeds the dielectric strength of the insulating material, the partial discharge phenomena will be occurred. And once it is occurred, it can introduce some physical and chemical changes which produce emission that can be detected by our measuring instruments. And as far as when if you want to describe the partial discharge in a different terminologies, there are main three discharges which can be identified, like internal discharge, which is like a void or a cavity. Then it can be a surface discharge because of any dust or some improper finishing of the insulation surface. And the last but not the least is the corona discharge, which is almost very common in case of a substation. So these are the multiple ways that it can be manifested. Then now we understand that what exactly the partial discharge is, that it is a localized discharges which is partially bridges the insulation, but how it can affect the insulation and what exactly it does to the insulation material. So when we talk about if there is any PD is already there in any gas insulated switchgear, it is a gradual process which ultimately deteriorates the insulation, causing the sustained discharges and permanently damage the non-self-restoring insulation. And although this process is really slow, but if this phenomena is already measured, it tends to indicate that it will reduce the service life of electrical asset or a gas insulated switchgear. So how it is reducing the service life of the gas insulated switchgear? So there are several factors that is explained here. So whenever there is a PD, it is a kind of an electron bombardment at that particular place. So whenever there is a PD happening, it creates a hot plasma or a very high temperature at that localized point. And once there is a heat, that it is going to have some thermal effects. And because of that thermal effects, you have some changes in the chemical composition of the insulating material. And because of that, you are going to have a training effect. And over a period of time, when this string is increasing and increasing, and if this string reach to a complete breakdown of the insulation system, so ultimately it flashes over at the end, and it is like as good as a flashover on load. So, and when it comes to the GIS, this is one of the example which was taken from the Segre publications from the Segre publications, where they have given a photograph of a 145 kV GIS voltage transformer from the bursting disk. If you can see that how dangerous and how damaging this flashovers can be, or a PD can be in the GIS. So for an example, that was just 10 mm small particle which was left inside the GIS, and it can create a disaster like this. So it is really vital that we should remove any partial discharge which is happening in GIS. So we can prevent such flashovers and costly outages. So now the main important thing to understand that the GIS layout or a GIS design is very simple as compared to any other electrical assets. So if you can see over here, this is an example or a cut section of a double bus bar scheme of a gas insulated switchgear. So if you can see that the construction is really simple. The red and brown parts are the main high voltage and current carrying conductors. Then the yellow portion is a main insulation of the GIS, which is a SF6 case. And the blue portion is a grounded part of the GIS. So as a whole, the GIS is a very simple design. Then how can the partial discharge can be generated in the GIS? So for understanding or giving you some hints that what kind of partial discharge sources can be present in a GIS, this image can illustrate the same. So when we talk about the GIS, the conductors are supported by means of insulators. So if these conductors are and they are going to be connected through a bolts or with a bolt connections at that particular connections. So whenever if these connections are not properly tightened up or any of the screw is got loosened because of any reason, it can generate a floating electrode partial discharges. Then during the installation stage, if any particles, which is like as I shown in my earlier slide, if it is a very small burr of a aluminum left inside the GIS, it can generate a free moving, it is as good as a free moving particle or a fixed particle inside the GIS, and it can generate a good amount of partial discharge signals. Then as we have as a hard insulation, we have insulators inside the GIS. So if there is any kind of void which is present in the insulators, can generate a partial discharges as well. So, and last but not the least is the external interferences from the electromagnetic interferences from the atmosphere, and which can be like a radar, telephone, machine thyristors, or a corona signals, which can be coupled through the GIS bushings and can enter inside the GIS. So these are the several discharges which you can detect during the partial discharge measurement on GIS. Now, coming to the measurement techniques, that how we can measure these partial discharges in case if there is any PD happening inside the GIS. So as I explained, whenever the partial discharge is happening, it can generate or emits the energy in different forms, which can be optical, mechanical, electrical, or chemical. And whereas we are more concentrated on the mechanical and electrical way for performing the measurement on especially the GIS is concerned. So when we talk about the electrical measurement, there are two ways, which is one is the IEC 60270, which is a conventional way of measurement, and another one is a radio frequency measurement, which is can be in high frequency, very high frequency, and in case of GIS, it is almost the ultra high frequency. So this is several ways that we can perform the partial discharge on GIS, and the another way to perform the measurement by means of acoustic sensors, which is a mechanical way of performing the partial discharges. And we will see the further on this particular topics in upcoming slides. So now just to give you some brief example that what exactly the conventional or IEC 60270 test setup is all about. So whenever we are talking about the measurement as per the conventional measurement IEC 60270, we need to understand this is an offline test, and we have to powered up the equipment under test or a GIS by means of an external high voltage source. And the particular object is going to be connected through a coupling capacitor with an impedance circuit connected in parallel to it through our PD measuring system. And all these measurements are done as per the IEC 60270 defined frequency range of 40 kilohertz to 1 megahertz. But the important part of this conventional measurement is that what we can do with this circuit is we can do the calibration. So what do you mean by calibration? How does it going to help you? So let us give some example, like whenever you have a pulse generator which can simulate the 5 PC discharges, which is limit for the gas insulated switchgear, you can inject the charge at the terminal of the test object, and you can actually calibrate, or you can able to see the same amount of charge which is generated by the pulse generator on your measuring system. So as soon as when you are removing this pulse generator and you are injecting the high voltage through a HV supply equipments, and if any discharges which is generated in the GIS, you are going to see the same amount of discharges on your PD system. So by means of a calibration, you are identifying that if you have any kind of PD which is generating in the GIS, your measuring instrument will reflect the same amount of apparent charge on your measuring system. So this is advantage of IEC 60270 measurement, where you can perform the calibration and you can actually quantify the charge in terms of a picocoulomb. And now coming to the another measurement technique which we are more focusing when we talking about on-site test for the GIS. So the one is the radio frequency and another one is the acoustic measurement. So now we are coming to the UHF measurement. So the question arises that, okay, when we talk about the GIS, why we have to go for the UHF measurement? So just give you an example, if you have a sharp tip or or a a tip on your inner conductor of your GIS, and if you are injecting the voltage at certain point of time at this particular tip, the voltage trace is going to be higher, and it can generate a partial discharges at this particular point. And when the person called Alexander Jade and Martin Judd, who had did this who did this experiment in the laboratory, where they put such a needle on a high voltage conductor, and they captured the PD pulses which is actually generated because of this particular defect. And what they found is the rise time of this PD pulses, because of such kind of discharges in SF6, it goes up to 24 picoseconds. And when you are converting this picoseconds into the frequency, it goes to like 15 gigahertz. And now when we talk about GIS, the GIS is like a coaxial cable, as good as a coaxial cable. The design of the GIS is such that, and when you have a UHF antennas which are pre-fitted in the GIS, or you have any external UHF antenna to receive the signals actually can be transmitted in the GIS in different forms of EM modes, not only TEM00, but there will be a TE or TM modes as well. And because as the GIS have a different spacers, band and T connections, the signals have a discontinuity, or the signals can be reconstructed or deconstructed at different points. And these particular signals can be captured by means of ultra high frequency signals. So that is the reason that we use ultra high frequency measurement in gas insulated switchgear. And now the question arises that how many sensors, or how many UHF sensors, or which kind of UHF sensors we will require. So nowadays almost each and every GIS OEM is actually incorporating the UHF sensors already in the GIS, which can be also called as an integrated or embedded UHF sensors, and they have a frequency range of somewhat 100 megahertz to 2 gigahertz, which is ultra high frequency band. And as this particular sensors are already pre-fitted inside the GIS identity, it is going to have a best signal to noise ratio. And as I said, these are generally provided by the GIS manufacturers. And in other case, when you have a very vintage GIS where you do not have any provision for a embedded UHF sensors, what you can do is you can go for external field sensors, where if you have your epoxy insulator have a opening portion of your epoxy part which is accessible on your insulator connection, you can use actually your external flange sensors. And the important thing is you need a open part of your insulator, because the electromagnetic waves or signals cannot pass through the metallic body, but it can pass through insulation of your epoxy insulator. So you can connect the EFS sensor on your unshielded part of your insulators, or else if in earlier GIS, old GIS, we have a window for the opening inspection windows, which can be greater than 60 mm diameter. So if you have a greater than 60 mm window diameter, you can use a window sensors for decoupling this UHF signals from your for the PD measurement. But only thing to keep in mind is whenever we talk about the embedded or external sensors, the sensitivity of your measurement with the embedded sensors is going to be very high compared to external UHF sensors. So in case if with the embedded sensors you require a less amount of UHF sensors, but in case if you are using external sensors, it might be possible that you require more number of UHF sensors to be connected for the fruitful measurement. Now coming to the question is, whenever we are saying that when we perform the conventional measurement, we can quantify the charge in terms of picocoulomb. But when we talk about a UHF measurement, it is It is just like sensing the partial discharge signals by means of a sensor. So you cannot actually quantify the charge in terms of picocoulomb, but what you do is you are measuring the charge in terms of a ratio of dB microvolt or a dBm. So how I can conclude the measurement, what amount of partial discharge which I measured with the UHF sensors are whether greater than or equal to 5 pc or not. So or a less than or equal to 5 pc or not. So for that there is a special sensitivity verification procedure which is derived by the SIGRE working group, and it is called as a 654. This particular document is freely available on a SIGRE website. Only thing is you just need to register on your register with your mail ID on your on a SIGRE, and then you can actually download this particular document free of cost. So this is a very useful document, and you should read about the sensitivity verification procedure. And just to elaborate that what this particular document says is, there is a sensitivity verification two-step procedure is given, where the step one is a laboratory test. In a laboratory test, the GIS has the part of the GIS is taken where the pre-installed UHF sensors C1 and C2 will be presented in the GIS, and at the C1 sensor, one known defect, it can be a particle or anything, is placed in that particular as close as C1 sensor, and this particular test setup is calibrated by means of a IEC 60270 conventional measurement, and then the voltage is applied to this GIS by means of a high voltage source, and it is applied until this particular defect generates a 5 pc discharges, and that can be measured in the IEC 60270 test setup. And once this defect is generating 5 pc discharges, the UHF sensors, which is C2, is connected to the UHF measuring device, and this particular device can be measured by means of a spectrum analyzer or by means of our supplied PD measuring instrument, and the measurement is taken in terms of a PRPD measurement or a frequency spectra of that particular real 5 pc discharges signal. So, and after this, once this measurement is taken, the voltage is now no more applied to this particular GIS, and now we are coming up with the pulse generator, which is connected exactly at the C1, which can vary the impulse variable amplitude, which can be like 2 volt, 5 volt, 10 volt, 20 volt, depending on the different GIS manufacturer. This particular voltage is different. So, and what they do is they're injecting a 2 or 5 or 10 volts, and what they do is they try to superimpose the measurement pulses which is generated by this pulse generator with the UHF measuring device directly on the real 5 pc discharges. So if you can see on this image, you can able to see this, the black traces are superimposed by a green traces. So you can see this at 10 volts, it is exactly as good as having the 5 pc discharges on the spectra stream, and as well as with our measuring instrument, you can able to see this straight line which is actually generated because of this pulse generator having the almost same kind of amplitude which is generated by the 5 pc discharges. So this is how you can understand actually the sensitivity verification at step 1 procedure. And once you define that, okay, we need a 10 volt to perform the sensitivity verification. So in step 2, whenever you are on site with the GIS, what you can do is you can inject, you can connect our pulse, the same type of pulse generator which is used in step 1 procedure at one of the sensor of X2, and then you can connect your UHF measuring device on X1 or X3. And what you can do is you can take a ground noise before injecting the pulse generator, pulse with the pulse generator, and after that you can inject the pulse with the pulse generator, and you can measure the partial discharges which is generated because of this pulse generator on your X1 or X3 sensors. And what you can see is here you do not have any PD signals on your PRPD pattern, but here you have a lot of and same as in frequency spectra as well. And in at the bottom image in the frequency spectra, you can able to see ample amount of frequency signals and corresponding PRPD pattern where you can see this straight line which is becoming again because of this pulse generator. So once you do this for complete part of your GIS, that means you are injecting from one sensor and you are measuring at your adjacent sensors. What you can actually identify is for the acceptance criteria that each sensor needs to be pick up the signal at least once by injecting with the pulse generator, and at least the one measurement through each part of the GIS. So once all these measurement signals are captured in your measurement, what you can actually confirm is that the given measurement setup is capable of detecting all PD impulses of 5 PC or above. So once your sensitivity verification is completed, you can actually identify the number of UHF sensors adequacy and the sensitive measurement of 5 PC or above. So by means of a sensitivity verification, you are actually confirming that your complete measurement setup or a number of UHF sensor placed in GIS are adequate enough to measure the partial discharges of 5 PC or above. Now coming to the in summary of our up till now. So up till now what I discussed is about that how the PD can be occurred in case of a GIS, which is because of the imperfection or a defects. And once the PD is generated, it is emitting the energy which causes the deterioration. And once it is in the SF6, they are generating some kind of UHF signals which can be wave guided by the GIS enclosure in a complex propagation. And this particular pulse packages can be picked up by means of various sensors or antennas, which can be either embedded sensors or external UHF sensors. And the very most important thing about the UHF measurement that we cannot quantify the values in terms of picocoulomb. So for the acceptance testing, we need to perform a sensitivity verification. And by means of a sensitivity verification, we can actually identify that the measurement what we do is 5 PC or above. So I would like to take any questions up till now if any of the audiences have at this particular moment. Michael?
I guess we don't have any questions at the moment.
Okay, so then I would like to continue. So now coming to the next topic that okay, now during the measurement in IEC 60270 or a UHF, in IEC 60270 we actually quantify the charge in terms of a picocoulomb, so we understand that whether there is a 5 PC or not. And in case of a UHF measurement, we do the sensitivity verification and we know that okay, the values are sensitivity is matching. But how we can identify that what kind of partial discharge defect is generating the partial discharge? So earlier in earlier measurement, people used to perform the measurement with the help of an oscilloscope in a sinusoidal measurement or a elliptical way of measurement, where the signals are generated during the measurement are represent like this. But during the measurement, our eyes and brain cannot store the amplitude or a phase characteristics of these signals on a sine wave. So nowadays the technique called as the PRPD patterns, which is nothing but a phase resolved partial discharge pattern, are introduced, where actually this particular patterns are a 2D representation of a 3D array, where the x-axis is a time or a frequency, and a y-axis in case of a IEC 60270 measurement is a magnitude in terms of a picocoulomb, or in case of a UHF measurement it is dB microvolt or a percentage. And this particular third axis is known as a counts. So depending on how many times the pulses are generated because of the partial discharge, they are actually giving the phase position on the sine wave, which is denoted by a different colored form. So whenever the single pulse is captured, it denotes in a gray form. And as soon as the same pulse is repeating again at the same location, it will change the color to a red and then yellow if you put it for a longer period of time. It is just denoting like if you are hitting the iron at the start, very beginning, it will be gray, and as soon as you are hitting at the same spot, it will try to change the color from red to orange and then to yellow. So This is how you can find out the intensity of the partial discharges at that this particular point. And these patterns are also called as a phi QN pattern as well. And whenever we are talking about a different kind of defects which can be there inside the GIS, this all kind of defects like a floating electrodes, void, or a particles, they have a definite kind of a pattern which can be generated because of these discharges. So if I talk about the moving particle or a free moving particle inside the GIS, they are going to generate the pattern like this, which is shown on shown in the right side of this slide, where you can able to see this, that on the top pattern, the magnitude of the partial discharge is too high, whereas in the bottom pattern, the magnitude of the particle is little bit lesser. But what you can see is they have a same symmetrical pattern on both the half cycle of your sine wave, as you can see on the bottom as well, and they have a same kind of behavior in terms of a PRPD pattern. So whenever you are encountering such patterns during your PD measurement, you can judge that the pattern is generated because of a moving particle. And these are the several measurement which was done because of the floating potential partial discharges. So whenever if you have a something which has to be connected firmly to the high voltage potential or a ground potential in the GIS, and it is not connected firmly, or your contacts which is connected to the insulator are not properly tightened up, such kind of patterns can be generated. And once you got encountered any patterns like this, you can identify that this particular pattern is of a floating potential partial discharges. So then you know that what you should look for. And last, which is I want to give you an example of a void. If you have a void in your insulators, the pattern of a void will be look something like this. It is always a symmetrical on or your both of the sine wave, positive and negative half cycles. And if you see, they're mostly started on the zero crossings, and they have a eyebrow like shapes on your measured PRPD pattern. So when you are encountering any pattern like this, you should identify that this is coming out because of the void, and then you can identify that which of the insulator can be there in your in your GIS eternity. So once you measure the partial discharge by any conventional measurement or unconventional measurement, you need to identify the type of defect which can be done with the help of these PRPD patterns. And once you encounter these PRPD patterns, you can actually identify the which kind of source which is generating the PD. And once you know the source of the partial discharge, whether it would be a particle, a floating electrode, or a void, then you can actually jump into the GIS and you can find out the exact connections or positions where this defect can be lied up. So this is really important in case of analysis point of view. Now coming to the solutions, as a Megger, we provide that we have a different portable measuring instrument available with us. So whenever you are only looking for a ultra high frequency measurement on your gas insulated switchgear, we have a GIS Monitor Portable. This particular instrument comes with the minimum 8 channel, which is all connected at a single time, and you can do this parallel measurement. It can do the sync connection up to 20 to 300 hertz. So during the commissioning stage also, you can utilize this instrument for performing the partial discharge. And there are several accessories which is actually making us an advantageous thing to our competitors, which is IPU and FCU, which use I will explain in an upcoming slide. And then we supplying external DA2 antenna for eliminating or suppressing the external noise from the atmosphere, and the pulse generator, which is also called as a calibrator, for performing the sensitivity verification for finding out the adequacy of a number of UHF sensors. Now coming to this IPU and FCU, what we do is we are connecting our IPU and FCU directly at the point of the UHF sensor connection. And the advantage of this connecting the IPU and FCU is the IPU is actually protecting our frequency converting unit, and the frequency converting units is actually actually down converting the complete pulse packages of UHF frequency signals into the IEC 60270 signals. So whenever we are performing the measurement with our GIS Monitor Portable or any other portable instrument or an online monitoring system, we are not capturing any external noises which are lied in a very high frequency, which can be like a mobile tower signals or any other other radar or other signals which can affect our measurement. So, and by using this FCUs, it gives us an advantage that we can actually use the more number of length of the cable, which can be extended up to 80 meters. And unlikely our competitors which are using the UHF cables, we can use a normal BNC cables. So that is how we can actually do the fruitful measurement, and we can eliminate the noise at the by connecting our front end units directly at the UHF sensor connections. And these are the several examples that how we can connect this instrument on a already embedded sensors or external window sensors or external flange sensors on your insulators. So these are the connections, and the important thing is we are providing 8 channel for connecting the measurement all 8 sensors. And apart from these 8 channels, you have a 2 channels separate channels, which is one for the getting signal and another one is for the sync connection. So actually you have a 10 channel instrument which can be connected at a single time, and you can actually measure the 8 channel at the same time. Sorry. Now coming to the software part of this instrument, this particular instrument has to be it has a dedicated software, and it has to be operated by a laptop by connecting it to USB or a LAN connection. And this is the software screen of the instrument where you can see all the 8 channel connection on your single screen, and you can actually analysis the data, and you can identify that the signal is where the signal is more closer to which sensor depending on the magnitude of your measured signal. And there are several other things like a gating, LLD and phase shifts are given, which can be very useful for analysis purpose on a later stage. And apart from this instrument, we have another instrument called AIDA Compact, which gives you an advantage to perform the UHF measurement and acoustic measurement with the same with the single instrument. And this instrument are available in a different input channels like 4 or 12 channels depending on the customer requirement. And all these channels can be freely configurable to acoustic or a UHF measurement. And system has a brain which can detect that which kind of sensor is connected to the instrument, whether it is acoustic or a UHF. And as it is an acoustic measurement, you have a headphone or a speaker inbuilt on your instrument, which can actually simulate the sound because of the acoustic signals. And the accessories are almost as good as same what we shown in a shown during our GIS Monitor Portable. The only one thing is added is the acoustic sensors along with the preamplifier and the special fixtures for connecting this acoustic sensor on the body of the GIS. As the GIS body is curvature, we have a special SFX1 sensor fixture builds for this acoustic sensors. And these are the several examples that how this instrument can be connected to the GIS. So it can be connected to the external window sensors, external flange sensors, and last but not the least is the acoustic sensors. And you can always connect this instrument to the embedded sensors as well. So these are the several examples that how you can connect the instrument to GIS for PD measurement. And once you are connecting this instrument to GIS, the instrument has a built-in display which have a different display modes, where the first mode is a scope mode, where you can actually identify the PIPD patterns in a gray form directly on the instrument. Then you have a time display where you can actually identify the time of flight of if you have a particle inside your GIS which is already hopping or not. When it is hopping, you have a pattern like this. And if it is not hopping, the measurement comes down to this base level. So you can identify the particle is not moving. But in case you get the pattern like this, you can identify the particle is already hopping or moving inside the GIS. And the last display, which is a meter display, where actually you can identify the RMS and peak values of the PD amplitude. And apart from the measurement display, this particular instrument also have a dedicated software. So you can actually connect this instrument to your laptop, and you can actually prepare a report or drag out the data from the measurement. And the important feature about the software is you can actually convert this gray PRPD patterns into the colored form of PRPD pattern by use of this particular feature in the software. And apart from this, that will help you to actually do some more further analysis during your measurement. So the software is always advantageous. And now, so I would like to summarize for the portable measuring instruments up till now. So we have a two different instrument called GIS Monitor Portable and AIDA Compact. So both of the instrument have a different features. So GIS Monitor is mainly for UHF measurement, and AIDA Compact can be able to do the UHF and acoustic measurement. So now coming to the last solution which we provide for GIS, which is a continuous online monitoring system. So as you can see on the screen, this is a single line diagram which is corresponding to a architecture overview of the system, which I will explain you in upcoming slide as well. So we have a acquisition racks which are calling as a PDMAR, and this particular acquisition racks can accommodate 15 GIS monitor plugin boards. Each plugin boards have 8 measurement channels, so we can go up to 120 measurement channels with a one particular acquisition rack. And these acquisition racks are equipped with a cabinet surveillance unit, sync switching boxes for sync purpose, then any object running signal as well. And it has a backup UPS in case of a power supply failure. And such racks are available in a IP65 module as well. So in case if you have a longer bus ducts which are going outside the GIS, you can actually use this outdoor cabinets for connecting or monitoring the outdoor UHF sensors. Then all the connections from the acquisition racks are connected to the PDMCR racks by means of a FO cable, and these connections can be interfaced to IC61850 interface, and it has a relay output connection or LRM as well. And this particular racks comes with the comes with the printer and a UPS and a self monitoring display as well. So prior going to the software or a HMI feature, I would like to just brief you about this complete architecture of the system. So from the UHF sensor, either it can be embedded or an external UHF sensor. Our FCU and IPU are connected directly at the sensor connections, and the normal coaxial cable, which is for the indoor RG58 or for the outdoor RG142, is connected to connected to the our front end units, and they are routing through the acquisition racks. And all these acquisition racks are depending on how big the GIS is. If your GIS is too big, or you have a more number of UHF sensors, the number of acquisition racks will be depending on the size of the GIS. And all this cable connection routed through acquisition racks, and from the acquisition racks only one fiber optic connection is connected to a main controlling rack, and this controlling rack can be there situated in the substation control room. So as you can see, we are forming the ring network of a fiber optic to increase the redundancy during the continuous monitoring purpose. So if any of the connection is got broken, still we cannot lose the signal from that panels to our controlling racks, as they are connected in a ring format. And as I explained, from the control rack, you can take the data remotely in your central substation monitoring system or your SCADA, or if you provide the internet on your PD monitoring control rack, then we can actually take access of this panel, and we can actually do the analysis remotely as well by sitting at any corner of the world. So this is about the complete architecture of our system. Now coming to the software. So when we are talking about the control rack, on the control rack screen, you can able to have a GIS diagram of your GIS same on your software screen. And all the PD sensors which are there, or UHF sensors there on your GIS are labeled like this on the screen. So whenever you want to see any activity on your any of your sensor, you can just click on the sensors and it will redirect you to this screen where you can actually identify this, the particular sensor is synchronized by the external frequencies which are connected from the which are actually present on the GIS, and you can actually identify the QP or NQS level of the partial discharge over a period of time on your same screen. So actually you can identify the partial discharge, whether it is happening on your that particular sensor or not, which will give you in terms of a PRPD pattern as well. Then all the event which is generated during your your online monitoring system. So let us say if you already putting some alarm or warning level in your measurement, and if the particular sensor exceeding that value, that particular sensor will be captured at this particular tab, and it is going to have a date and time stamp at the same time along with the PRPD pattern. So you can actually know that at what particular time the partial discharge was exceeded the threshold limit on that particular sensor. And apart from this, the system is continuously monitoring the data for all the connection as well. So if you have any connection issue on your measurement chain, it will reflect it in a general data event where my cursor is moving at the point of time. And last tab here you have a status. So if you have a more number of panels which are connected to a fiber optic ring, so if any ring network is broken, this will turn to red. And if any fuse or any UPS or a fan is not running in your any of your cabinets, the main HMI will give you a alarm which is almost have a date and time stamp in this general event, as well as you can able to identify on a status tab as well. Apart from this, you can always take this particular software in an offline mode, and you can identify if you have any PD signals which are already there, which are not cross the threshold value of an alarm or warning, but you can identify if there is any activities happening on your any sensors. So you want to do some periodical checks also with the continuous monitoring system, you can do that as well. And this particular the very important feature of our instrument is it comes with a dedicated sensitivity and a high voltage test mode. So this same instrument you can actually use during the commissioning stage of a GIS as well. So during the commissioning stage, you can perform the high voltage and partial discharge measurement with the help of our monitoring system. And now after explaining you the features of our portable and continuous monitoring system, I am coming to the almost the second last slide of my today's presentation, which is ICM Expert software. So now, as we know, we all are not the PD experts, and how we can identify the measured PRPD pattern is coming because of what kind of defect. So we have a software which called ICM Expert. So you can capture the data with your portable or monitoring system. You have a PRPD pattern, so you can put that PD pattern in your ICM Expert software, and once you do the analyze, we have a database structure fed in this software, and it will try to identify the closest match to this particular PRPD pattern, and it will give you the hint that this particular pattern is generated because of a particle or a void or a floating potential. So this gives you a first level of support to identify that what kind of partial discharge defect is generating the partial discharges in your GIS. And so this is about the ICM Expert software. And if you want to do some more research or understanding about this particular subject, where you want to learn about the on-site PD measurement techniques for gas insulated switchgear or any of your electrical asset, you can refer any of this document, which is like IC 62478, the SIGRE 662 or a 444 or a 502, and the sensitivity verification, which is 654. You can actually get more of the knowledge about that how you should perform the measurement on with the help of these documents. So with this slide, I would like to conclude my today's presentation on gas insulated switchgear. And now we can open the forum for question answers. So I would like to request you, if you have any questions, you can post on the chat box, and we can answer the questions questions with the best possible satisfactory answers.
Okay, thank you so much, Kiyor, for that excellent presentation. And before we move on to the question and answer portion, let me remind you that we have a pop-up survey. When you close the screen of this webinar, you will have a pop-up survey. And please answer that, and that would really help us a lot in improving our future webinars. So now let's move on to the question and answer. Kiyor, the first question is, which the best method we can apply in GIS? Kiyor?
Sorry, I was muted. Yeah, I heard the question. So I would like to answer in this way. If you are performing the measurement in the factory, the best method to perform in the factory is a conventional one, which is the IC 60270 setup. But now when we are talking about on-site measurement, which is you have to perform the partial discharge on site on a real on-site conditions, the important measurement to perform the partial discharge is a UHF technique. So with the help of a ultra high frequency measurement, you can actually identify the all kind of defects which can be generating the partial discharge in GIS.
Okay, thank you for the answer, Kiyor. Another question, maybe a follow-up question. Is that safe with induction on GIS 500 kV or above?
Sorry, can you repeat your question again?
Yeah, he's asking if it is safe with the induction on GIS, which is rated 500 kV or above.
Yeah, that is, you can actually do the connections because this UHF sensors are there to measure the partial discharges. And the only thing you need to consider is you should be more careful at the interfacing points like the bushing, which is connected to the overhead lines, or let's say a cable connection which is connected to the GIS. At that particular points, you need to be more careful. Otherwise, you can connect your UHF sensors by opening the caps, and you can connect the instrument for UHF measurement. It is completely safe.
Okay, yeah. Thank you for the answer, Kiyor. We have another question here. Maybe he's referring to slide number 15. In case GIS is energized, integrated UHF sensor to connect our equipment need to shut down.
Just a second. I will jump to the slide number 15 first. Okay, so slide number 15 is about the integrated or embedded UHF sensors. So the question is, for this implementing this embedded sensors, do we need to take a shutdown? The answer is yes. If you have to integrate the embedded sensors, you need to take a shutdown, because as shown in this image, this particular sensors are a part which is going inside the GIS. And if you see this I will go to this screen where you can see this. The sensing element is almost in line with the GIS body. So this is part inside the GIS eternity, and it is covered by the SF6. So for implementing the integrated UHF sensors, you need to take a shutdown, and you need to do some gassing activity as well. But in case you're going with the external sensors like EFS or Windows sensors, you don't need to take a shutdown, because these are connected. This can be retrofitted without opening of the GIS.
Yep. Thank you, Kiyor. This one is related to the 500 kV induction question. Maybe he is referring to could it affect the measurement if we have induction at the 500 kV system?
The answer is no, because when we are talking about the induction means it is almost like a corona or a high voltage stress. And if it is when we talk about induction, it is almost in a air. And as we know, the air is mainly a nitrogen. And if you have any induction in the air, the frequency can be last up to less than 350 megahertz. And when we are talking about the ultra high frequency measurement, which goes up to 200 megahertz to 2 gigahertz. So this particular induction cannot be affect much in your measurement.
Great. Thank you so much for the answer, Kyo. So guys, if you have any other questions, just type it in here, or for any of you who have further questions, you can send us an email also. Thank you so much, Kior, for your time here in Asia. And guys, thank you so much everyone for attending this webinar, and hope to see you again next time. We still have a lot of we still have a lot of webinars to come. So